Okay, I'm just because there's a amount of stuff we need to get through today before you can do any more problems. I'm not going to answer any homework questions today, but tomorrow I will. So think about that if any of the homework problems you get stuck on or whatever. Okay, so at the end of last time, we've been talking about the relationship between position, velocity, and acceleration. And we talked about how if you're going in the direction from acceleration to position, to velocity to position, you need these constants of integration because it's a integration that goes in that direction. And at the end of last time, we finished by talking about constant acceleration. Like, what do you know if you have a case where the acceleration is constant? That's an important special case. Um, okay, so what we did to start to figure out what we know with constant acceleration is we said this acceleration function is just equal to a constant, a, and if you integrate once, so if you're given that the velocity at time 0 is equal to the constant v0, then integrate that acceleration function and you get velocity as a function of time is equal to at plus v0. And if you integrate that one more time, we didn't go through this before, but I think this is something that you're asked to do on the homework, but it's just integrating again and using the boundary conditions. But if you're also given that when time is equal to 0, position is equal to this constant p0, then position as a function of time is equal to, you know what, let me write this the other way. I'm just going to rearrange these. I'm not changing the meaning of anything, but I'm just going to put it in the form that you'll see more often. So just the order of v0 in the other term. And doing it the same way, the position function is p0 plus v0t plus 1/2 a t squared. And you get that from just integrating the equation 1 there. And then the third step, sometimes it's easier to deal with relationships that don't have an explicit dependence on time. So if you use the two equations above, and substitute one into the other one, you can come up with this expression that's like 2 times a times the quantity position as a function of time. Actually, let me make this a square bracket. So 2a times the quantity, p minus p0 is equal to v as a function of time squared minus v0 squared. So this is where you do these kind of problems, and instead of knowing explicitly what the time is when you want to calculate one of these variables, you're given, say, well, we know the velocity is 30 meters per second. Can we use that to figure out the position or vice versa? So I think both of those are things that you're asked to do in the homework. Okay. What's the most important case, the case that's going to come up most often of constant acceleration? Yeah, the most important case of constant acceleration is free fall. And when I say free fall, I'm including projectile motion. I'm not talking about something necessarily just falling straight down. That's also by, well, what does free fall mean? Projectile motion mean? Um, it means that the only significant force um, acting on the object is gravity. And this brings up, there's going to be three of these over the course of the semester. This is the first one, common misconception number one. So in this class, there are a lot of things that you might not have known how to deal with mathematically, but your intuition sort of tells you how it works, and you can sort of trust that. This is the first case where most people's intuition is wrong. And, and so in a case like that, it takes a little work to go back and try to rewire the parts of your brain that over decades have been telling you, you know, that that the world acts in a certain way and it's not actually how it is. So common misconception number one. By the way, these are all going to come up in quizzes. So every quiz, remember these. Um, Often believed, and even by uh, the best scientists of the time for a very long time, uh, things like things like this were believed. Aristotle had a horrible misunderstanding of this, so it's not a thing about you know being dumb. It's just it's confusing. The way what we see in the world is confusing to interpret. I often believe that objects objects with greater mass fall faster than objects with smaller mass, with less mass, due to gravity. So, in other words, gravity itself does something to make a rock fall faster than a ping pong ball. Okay. Well, this is why it's confusing because if you go to the top of a building and drop a rock and a ping pong ball, the rock is going to hit the ground faster. Okay. And gravity is what makes them both fall. So it's sort of a natural thing to believe that gravity is making the rock fall faster. That's not it, though. Really, so in fact, um, gravity by itself makes all objects fall the same. Um, Differences between objects are all due to air resistance. Okay, so um, if we could set up an experiment where there was no air resistance, that's the vacuum. And I don't know, like maybe you hear people sort of joke about this too. I don't know. I remember like my dad always thought it was funny. Like when I was first taking physics in high school, he'd always be like, "Oh, well, yes, I'm sure that's true in a vacuum or whatever. Like where do you have a vacuum? You know, like what would happen if we were walking around in a vacuum right now? We'd all first our insides would explode out because there'd be no external pressure, and then we'd die of suffocation. You know, so it's not a very realistic environment. Um, but but yeah, if you have a vacuum, there's no air resistance on anything. You can drop a feather and a bowling ball, and they'll both fall to the ground exactly the same. And I'm going to show a video of that. It's super cool um, relative to other physics things, you know, not compared to like normal life things. Um, so why does air resistance treat different things differently? Uh, so um, so here's a list of the things determine how much air resistance affects motion. So the things that are high in air resistance affecting their motion, if you drop it, it's going to go slowly, um, like a feather or a piece of paper. And I'm not going to do this super mathematically. I'm going to do it in kind of like a intuitive way. You know, if you want to know more about it, I can show you like an equation that actually measures it, but I don't think that's really necessary for this. Um, so the first one is the object's mass. And this is where that misconception comes from. Um, so if everything else is equal, all else equal, um, a more massive object is less affected by air resistance. Um, so if you think of two things that are the exact same shape, um, but different masses, like I think intuitively, like a ping pong ball and a pinball are a good example. They're basically the same size. They're both round, smooth things. But you drop them both off the roof of a building, the pinball is going to hit first. And it's because everything else is the same, but the pinball has more mass. And so it's less affected by air resistance. Anyone have any questions about that? Um, the second thing is the object's speed. Um, so again, all else equal, A slower object is less affected by air resistance. So when you talk about like a space shuttle being in danger of burning up on reentry into the atmosphere, why is it only when it's on reentry into the atmosphere? On its whole way out of the atmosphere, it had no problem. No one was worried about it. It's just because at the time that it comes back into the atmosphere, it's going screaming fast, and so on the way out, no problem. Like the space shuttle, like when you're driving, pulling it behind a truck on the highway, you're not worried about it bursting into flames. But when it's going really fast and all of a sudden hits the atmosphere, um, air resistance has a huge effect, you know, and that leads to a lot of heat. Um, and then the third one is, well, the shape of the object. A little more than just area, but let's think of it that way. Um, so there are also shape effects even when the area is the same, but um, all else equal, um, an object with less area exposed to the air is less affected by air resistance. Um, and that's how a parachute works. When a parachute spreads out, it exposes a huge amount of area to the air perpendicular to the direction of motion, and all of that creates a huge amount of air resistance, which slows the thing down really fast. Okay, slows it down really easily. Um, and the bottom line of all this is if the effect of air resistance is negligible, all objects near the surface of the Earth accelerate down, that's toward the center of the Earth, at 9.81 meters per second squared. Okay, so when an object is not touching anything else, okay, uh, so an airplane in the sky or a helicopter or a ball that's falling, all of those, the thing is not touching any of its surroundings. There are really two forces acting on it. There's a force applied by the air, okay, which is either can be huge, sometimes it can have a very small effect. And then the second force is the weight, okay? And if something's falling straight down, like you just drop something off a cliff or something, the weight force, well, the air resistance force is always in the opposite direction of the motion. So if you drop it straight down, there's an air resistance force up and a weight force down. Okay. And so you've heard of terminal velocity. Everything has a terminal velocity, but you know, this kind of stuff about the effect of air resistance determines how high or low that terminal velocity is. But what the terminal velocity is since air resistance increases as the speed increases, okay, and as the thing falls, it's getting faster and faster, okay? Little by little, the air resistance force is going up while the weight force stays the same, okay? And eventually, any object gets to a speed where that air resistance force is exactly equal to the weight force. And when you have a weight force and an air resistance force that are equal, from that point on, it just moves with a constant velocity. There's no more acceleration. So that's the idea of terminal velocity. And a ping pong ball has a very low terminal velocity. A pinball has a much higher terminal velocity because of this kind of air resistance stuff. Okay, so and in the cases where you can ignore air resistance in the motion, that's the acceleration, no matter what the thing's doing. This is also sort of weird to get used to, but we'll get a lot of practice. So when you throw something up into the air, when it's on the way up, what's its acceleration? It's down, yep. And when it gets to the top of its motion and it's instantaneously at rest, what's its acceleration? Same. And when it's on the way back down, what's its acceleration? Same. The acceleration just never changes, okay? And it makes sense out of that. Think about what we talked about in lab with speeding up and slowing down. So when you throw something up into the air, throw a baseball into the air. Yeah, always. So is it speeding up or slowing down on its way up? Slowing down. So let's think about the directions of the velocity and the acceleration. It's going up, so its velocity is up. Its acceleration is down, and that's why it's slowing down, okay? And then once it starts coming back down, what's the direction of its velocity? Down. What's the direction of its acceleration? Acceleration is down. It's always down. And now they're moving in the same direction, and that's why now that it's coming down, it's speeding back up. Okay? So acceleration never changes. And probably on some quiz sometime during this semester, I'll write when a ball's on the way up, what's the direction of its acceleration? When the ball's on the way down, what's the direction of its acceleration? And a lot of people will, maybe this is a semester, it won't happen, but generally, like a lot of people get that wrong. So it's confusing. It's confusing, but try to beat that into your head. Okay, so now let's watch. So this video I'm going to show is they go into a giant facility that's designed for testing aircrafts, and they can suck all the air out of this giant thing, which is amazing. And once you suck all the air out of this giant room, they hook up a bowling ball and a feather to the very high ceiling and let them go. And you expect to see the bowling ball smash down to the ground and the feather flutter down, but that doesn't happen. They just fall and hit the ground, and the bowling ball smashes into the ground, and the feather bounces off the ground like it's made out of like rubber or something. It's really cool to see. Okay. And the thing is, if you take away the air resistance, any two things fall exactly the same. They did a version of this on the moon landing too, but it's the video's grainy. It's old quality video and it's hard to see. So, okay. Let's see, do I have? Come on, Brian. Talk to me.
Near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left.
2 grams of air left
And
in that
it's
whole place.
kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems. And that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one.
What we're watching so far, is the air in there or has it been pumped out? It's in there, and you can tell because he has not exploded and he can breathe. Okay? Then they're going to take him out before they pump the air out. Okay.
And drop them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Isn't that cool? I wish they would show it full speed. They never do, but so this,
Look at that.
They came down.
you didn't even see the feathers like flutter or anything because there's no air to make anything flutter.
Exactly.
Back on the side.
Exactly the same.
Feathers don't move, nothing.
Look at that. That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down. Gravity.
All right, so in this class, when we do free fall calculations, we're always going to be assuming that air resistance is negligible. And there are a lot of cases where air resistance isn't negligible, so like the kind of calculations we're doing wouldn't be applicable to feathers under normal conditions or ping pong balls that are moving reasonably fast or anything like that. So when you do these free fall problems, especially when you apply this idea to things outside this class, you know, if you're trying to actually calculate something that's going on as you know, that you see, you have to ask yourself, are there conditions present that make air resistance matter? You know, is the thing very light or very large surface area or moving very fast? And if those conditions are present, then your results aren't going to be very good. Okay, let's do an example problem. So let's say that you're at the top of a short bridge. Um, um, and you don't have a tape measure long enough, but you want to know how high the bridge is. So you drop a rock into the water, and it takes 0.80 seconds to hit the water. What's the height of the bridge? Okay, so here's the side of the bridge. Um, here's you dropping you're just trying to get your hand to right at the height of the bridge. So you drop this rock. Here's the water. Be sure there's not a boat under there. And now, remember, before we can talk about position as a function of time, we need to make a few choices. We need to choose what our zero position is, what our positive direction is, and what our zero time is. Okay, we'll choose, might as well choose time equals 0 to be when it's dry. Um, position equals 0. We could do this a couple ways. I normally choose the 0 position to be sort of at the lowest point in the problem, and then I choose the positive direction up. But you just have to be clear to yourself about what that choice is. We could do the same thing, put our 0 position at the point where the rock is dropped, put the positive direction down, and we'd get the same information out of it, although the numbers that we calculated would look a little different. We'd have to think about it to make them match up. So position equals 0, I'm going to say it's at the water. In the positive direction, I'm going to say it's up. Um, and I'm going to use the equation that says position as a function of time is equal to the position at time 0 plus v0 times the time plus 1/2 a time squared. Which of these do we know? Well, the time that we want to calculate this is when it hits the water. So this t is going to be 0.8. What's the velocity of the rock at time equals 0? 0, yep. So this is 0. What's the acceleration during this motion? And it's negative because our positive is up. If we would have chosen our positive direction down, it would be positive 9.81. This negative sign is important. And what's the position at time equals 0? Our 0 is at the water. At time equals 0, it's up at the top of the bridge. So this is the one we're trying to calculate. Okay, so we're trying to figure that out. Oh, there's one more thing we have to put in here. What's the position at time equals 0.8 seconds? Right. Because our 0 is the water, and that's when it hits the water. Okay, so now our equation says 0 is equal to P0 plus 0 times something is 0 plus 1/2 times 9.81. You can keep the units in the calculations if you treat them like algebraic variables, and they'll all cancel out. I'll show you how that works, but you don't have to do that. Times 0.8 seconds squared. So in this last term, the second squared cancels with the second squared there cancels with these seconds in the parentheses are going to be squared, so those go away. And so we get 0 is equal to P0 minus, what's 4.905 times 0.64? Can someone punch that in? Yeah, I just already have the negative there. Anybody have a calculator?
You want me to calculate everything?
Just that third term. Yeah, just 3.924. Anybody have confirmation on that? And the units, all we're left with is the meters. Oh, 1394? 139, okay. So 14. Okay. Okay, so P sub 0 is equal to about 3.14 meters. So that's how high the bridge is, 10 feet or so. Any questions about that? Okay, so now I'm going to do this again. This time with the 0 position at the top of the bridge. Top of the bridge. And the positive direction down. So again, I'm going to use the equation that says P of t is equal to P0 plus v0 times t plus 1/2 a t squared. And I didn't change anything about my time equals 0, so these are still going to be 0.8. It's still released from rest, so this v0 is going to be 0. What's the acceleration going to be this time? Yeah, so now our positive direction is down, and acceleration of gravity is down, so it's in the positive direction. So this is positive 9.81 meters per second squared. What's our P0? This time our 0 position is where it's released from, so that is P0. And so this time we know this one. And what's P of t? What's the position at 0.8 seconds? We don't know that. This is what we're trying to calculate this time. So position is equal to 0 plus 0 minus 3.14 meters. Plus, sorry. Yes, thank you. Yes, plus. So this is, I guess, I'll write this the position at 0.8 seconds. That's not times, that as a function. So the position is 3.14 meters positive. And so what does it mean now that the end, the rock, is 3.14 meters in the positive direction from 0? Since our positive is down, it means it's gone 3.14 meters down, which is the same thing as saying the bridge is 3.14 meters high. So the rock has traveled down 3.14 meters. So the bridge is 3.14 meters high. Okay, so in these kind of problems, in any kind of problem where you're going from a description of something happening in the world to a mathematical description, that choice of the positive direction and the 0 position and the 0 time, or those 3 choices, are important. Okay, you're going to have to do that. And depending on how you make those choices, your numbers are going to come out a little different. Later, when you interpret your numbers, you get the same story. You know, in both of these 2 cases, we figured out that the bridge was 3.14 meters high, but the values of our variables changed based on what we, you know, how we made those choices. Okay, so I think about one thing. Go back to an example we did on Thursday. The one where we were given that we were given that the velocity as a function of time is equal to 3t squared. Okay. In this one, why didn't we have to make choices about the zero position and positive direction and stuff like that. And the answer is, if you deal with problems that entirely, right from the start, live in math world, you've already been given the connection between the math and the whatever we didn't even talk about what kind of object that was, then it's already been done for you, okay? That start out with P of t, V of t, or A of t given, have already made these choices for you. Okay, so you need to make those choices of the zero position, the positive direction, and the zero time only in the step where you're taking a description of a motion in the world and putting it for the first time into math equations, into variable values. Okay. So let me give you two more two facts that will often be useful in free fall problems. If an object is dropped, then at the instant it's released, its velocity is the same as the velocity of what it's dropped from. Okay, so if you're in an elevator and you drop an object, at the instant you release it, that object's velocity is the velocity of the elevator. Okay, so if the elevator is going up, the thing has a positive velocity at that instant. If the elevator is going down, it has a negative velocity at that instant. Okay. If you're on a bridge, like in the example we did, and you let it go, that starting velocity is the velocity of the bridge, so it's zero. Okay, hopefully. Any questions about that? Right now, we're only doing one-dimensional problems, motion along a line, but when we get to two-dimensional problems, that'll work like if you're driving a car at 60 miles an hour and you hold something out the window and let go of it. At the instant you let go of it, it's moving in the car's direction at 60 miles an hour. Which is why, mathematically, maybe that wouldn't occur to you right away, but you do know intuitively that you don't want to jump out of a moving car, and that's why, right? You know that. Yeah, don't do that. Yeah. Hey, Bill, I got to cancel for this afternoon. I'm not doing that. Okay. Yeah, we're going to draw straws. We only need one person to do it. And then the second thing is when an object reaches the highest point in its flight. So if you throw something up into the air, the velocity is 0. And so what's happening is you throw something up into the air, it's slowing down, and right at the top, it's slowed down all the way to 0, and then it starts speeding up in the opposite direction. And so we'll use both of these in a lot of these problems. Anybody have any questions? Okay, we'll do a bunch of examples next time. Hi, yeah.
I have a question. Like, I know